The research discusses the difference in charge-voltage relations between ordinary and fractional capacitors. It begins by highlighting the debate in the time domain multiplication or convolution of capacitance and voltage determining charge in ordinary time-varying capacitors. The authors implemented a time-varying capacitor in parallel with a resistor using a motor-driven potentiometer and op-amps, finding a power law function response over 2 decades of time, confirming the time domain multiplication model. This is in contrast to the common interpretation of constant phase elements, CPEs, in time and frequency varying capacitors. The study then delves into the theoretical aspects, including the current charge relation and the voltage-current relations corresponding to the two alternatives. It also discusses the temporal responses of linearly increasing capacitance, highlighting the difference between the forced and unforced solutions. The research concludes by reporting measurements that distinguish between the time domain multiplication and convolution models, supporting the former and explaining the differing results in the literature. In the context of circuit theory, a time-varying capacitance is examined through 2 different models, the multiplication relation and the convolution relation. The first model, described by equation 5, leads to a voltage response that follows a power law function, as shown in equation 9, where the exponent is alpha 1. This response can be observed in the circuit depicted in figure 1, which consists of a time-varying capacitor in parallel with a resistor. The second model, represented by equation 6, results in an exponential response, as seen in equation 12, with a time constant of tau. To determine which model is valid for a time-varying capacitor, one must analyze the voltage response to a current impulse or an initial voltage and compare it to the power law response of equation 9, or the exponential response of equation 12. If the response follows a power law, the exponent should be checked to confirm whether it is alpha 1 or simply alpha. The constant phase element, CPE, another circuit component with a long history dating back to Cole, is defined by its impedance in the frequency domain, as given in equation 13. The equivalent capacitance of a CPE is described by equation 14, which simplifies to an ordinary capacitor as alpha approaches unity and to an ordinary resistor when alpha equals 0. Inverse Fourier transformation of equation 14 yields equation 15, representing the time domain equivalent capacitance. The current voltage relation for a CPE is expressed through a fractional derivative, as shown in equation 16. This element is crucial for understanding complex electrical behaviors and has been used in various applications, including electrochemical systems and biological tissues. Here is a combined summary of pages 5 and 6 of the research paper. The charge-voltage relation for a constant phase element, CPE, is derived by combining equations 4 and 16, resulting in equation 17, which reduces to the ordinary capacitor case when alpha equals 1. Solving for the charge, equation 19 is obtained, which is a convolution description of the CPE. In contrast to the ordinary time-varying capacitor, the CPE's charge-voltage response is uniquely defined by a convolution in time due to its frequency domain definition. The CPE is an idealized circuit element, with a singular relative permittivity given by equation 20, which can be viewed as a limiting case of well-behaved standard dielectric models, such as the Havroliak-Nagami model. The CPE can be found in the limit from the Havroliak-Nagami model, the Cole-Davidson model, or the Cole-Cole model. Focusing on the Cole-Cole model, the time domain current step response is proportional to the response function, phi t, given by equation 22, which has a small time approximation that corresponds to the Curie-von-Schweidler law. Similarly, the charge step response is proportional to the relaxation function, psi t, given by equation 23, which has a small time approximation that corresponds to the Kohlrausch law. The inductive CPE is defined by equation 24, which can be considered as a capacitive CPE with alpha equals alpha. Its temporal response is similar to that of the capacitive CPE, with voltage proportional to t caret alpha 1 for small temporal arguments. The similarity with the temporal response of the linearly varying capacitance is striking, indicating one way of implementing a CPE. The results reported in this section were found during an attempt to create a circuit with the same voltage response as the inductive CPE, exploiting the similarity in responses. The circuit realization is discussed in the following section. Here is a combined summary of pages 7 and 8 of the research paper. The authors propose an improved implementation of a time-varying capacitor using a voltage-controlled resistor, which is realized by a potentiometer mechanically coupled to a stepper motor. The stepper motor is controlled by a microcontroller programmed in the Arduino environment. This setup allows for a precise time-varying resistor to be realized, although it is slower than a JFET-BASED implementation due to the physically moving parts. The circuit diagram is shown in Fig. 2. The components used in the implementation include a Born's 91A1AB28B20 potentiometer, a 28BYJ48 stepper motor, and an Adafruit Metro M0 Express microcontroller. The capacitor is composed of 8 ceramic capacitors with a nominal value of 10 microfarads in parallel, resulting in a total capacitance of 87 microfarads. The op-amps used are not critical, with a high open-loop gain, high input impedance, and low output impedance, and the LM358 dual op-amp was used with satisfactory results. The measurement of the voltage response versus T was performed using a 16-bit analog-to-digital converter connected to a separate microcontroller and sampling at 860 Hz. The motor-driven potentiometer was first connected to a DC source and verified to work as a linearly varying resistor, with a rate of change of resistance phi equals 41.3 kΩ per second. The time-varying capacitor is given by the value of the feedback capacitor C and the Miller effect. The negative voltage gain of the two unity gain amplifiers and the potentiometer combined is given by equation 26, and the input impedance as a function of the impedance of the feedback capacitor is given by equation 27. When the capacitor C0 is taken into account, the equivalent capacitance is given by equation 28. The coefficient of variation of the capacitor theta is given by equation 29. The results of the measurements are reported in Figs. 36, showing the voltage response to an initial input voltage for different values of the parallel resistor. The time before the curves start falling represents the time constant of the circuit. The paper discusses the voltage response of a parallel combination of a resistor and a linearly increasing capacitor, with the goal of confirming the two-term time domain multiplication definition of current in a capacitor. The experiment involved measuring the voltage across the circuit over time, using different values for the parallel resistor, Rp, while keeping the capacitance, C, constant. The results are presented in figures 3 and 4, which show the measured voltage responses for Rp values of 150 kΩ and 82 kΩ, respectively. The expected alpha values were calculated using equation 30, which is derived from the theoretical model of the circuit's behavior. These expected values are compared to the estimated alpha values obtained from the measured data using equation 31. As shown in Table 1, there is a good correlation between the expected and estimated alpha values, indicating that the theoretical model accurately predicts the observed behavior of the circuit. The figures also demonstrate that the relaxation follows a power law for about 2 decades of time, confirming the validity of the two-term time domain multiplication definition of current in a capacitor. This is in contrast to the constant phase element, which when interpreted as a time and frequency varying capacitance, follows the time domain convolution of equation 6. The paper concludes that the measured voltage response matches the expected power law behavior predicted by the theoretical model, providing confirmation that the two-term time domain multiplication definition of current in a capacitor is correct for this circuit. This finding is consistent with previous studies, 2, 3, 4, and contrasts with the behavior of the constant phase element, 1, 5. The study's results contribute to a deeper understanding of the electrical properties of capacitors and their role in complex circuits. The authors present a comprehensive analysis of the constant phase element, CPE, and its distinction from time and frequency varying capacitance. Figure 5 demonstrates the results with a parallel resistor of 68 kΩ, showcasing the fundamental difference between the CPE and time and frequency varying capacitance. The discussion is supported by a range of references, including works by Eirik et al. 1, 5, Holm et al. 2, Geltsema, 3, Ortigara et al. 4, and others. These references provide a foundation for understanding the CPE and its relationship to capacitance, covering topics such as time domain and frequency domain definitions, circuit equivalence, and capacitor theory. Figure 6 presents results with a parallel resistor of 47 kΩ, further highlighting the differences between the CPE and time and frequency varying capacitance. The authors draw on additional references, including Pondy et al. 6, 7, Eirik et al. 8, Cole, 9, 10, and Westerland et al. 11, to explore the connections between the fractional derivative, Leibniz creep law, and non-Newtonian time-varying viscosity. The analysis also touches on the Curie-von Schweidler law and the fractional capacitor, with references to Das, 12, and others. The authors demonstrate a deep understanding of the underlying mathematical concepts, including Tikhonov regularization and deconvolution, as well as the physical principles governing the behavior of electrochemical capacitors. Throughout the discussion, the authors carefully distinguish between the CPE and time and frequency varying capacitance, emphasizing the importance of accurate modeling and characterization. The work highlights the limitations of traditional capacitor theory and the need for a more nuanced understanding of the underlying physical phenomena. Future work will likely involve further refinement of CPE models and their applications in various fields. The summary begins with the discussion on the fractional differential equation for capacitors, highlighting the work of J. Mod. Phys. 2017. This is followed by the time domain characterization of the Cole-Cole dielectric model by S. Holm, 2020. The models of dielectric relaxation based on completely monotone functions are then presented, as described by R. Garappa, F. Mainardi, and G. Maioni, 2016. A simple configuration for realizing voltage-controlled impedances is discussed, as proposed by R. Sanani and D. Bhaskar, 1992. Finally, the transistor tester with an AVR microcontroller, developed by KHK Diaresis Ubbeler, 2021, is mentioned.